Well, welcome to this session of our real-time technology and applying real-time analytics. My name is Ken Gorton. With me is RJ Sunderman. We are product engineers on the real-time and big data team. And we're the team that's responsible for developing GeoEvent Server, among other technologies. So today we want to talk a little bit about what we refer to, what we mean when we talk about real-time analytics. And in the course of that presentation, this presentation will show you some examples of applying real-time analytics and looking at how we can analyze streams of information in GeoEvent Server. Quick look at what we'll cover in the session. We'll start out with an overview of our real-time technology using GeoEvent Server with ArcGIS Server. And some of its core capabilities and some of the key components that you'll work with in analyzing real-time data. And then we'll present a few use cases to you and show you a few examples of how real-time analytics can seek to explore the data and find answers and sort of cut through a lot of the noise that a lot of real-time data is, especially high volume data. We'll take a close look at a number of processors and how those processors work to examine the data that's coming through GeoEvent Server. And then finally, we'll wrap it up with a look at where you can find additional information, tutorials, and other sessions here at the Dev Summit as well. How's that sound? All right, so first of all, performing real-time analysis with GeoEvent Server is, you need to really start out with ArcGIS Server because that's the foundation for GeoEvent Server. It always resides with ArcGIS Server. Now, the real-time capabilities for ArcGIS Server generally fall into these three categories, and the first of those is getting real-time data ingesting the data just as fast as it happens, and then being able to interrogate it and process that data is the second of those categories. And the third category is generating output streams of information from GeoEvent Server. And these output streams might be notifications that something has happened, or it might simply be logging information in a geodatabase, or a number of other things. Sending social media, for example, is one of the output stream capabilities. Now, because real-time data is very closely related to big data, there are a number of companion capabilities that are also enabled and supported in our real-time technology, such as the ability to visualize extremely large volumes of data without negatively affecting the performance of the client application. And still being able to make sense of the data. And another one is to be able to leverage some of the capabilities of the spatial temporal big data store beyond just that visualization, but being able to read, to write in and also read and query that information again, without the negative kind of performance that you might expect if you were to try and interact with big data in a standard traditional relational type of database. So a lot of that support goes along with it, and we work with the other teams, in the geoanalytics realm to sort of optimize a lot of the operations here across this technology. So first of all, a broad overview of what a GeoEvent service looks like, a geoanalytics service. In GeoEvent Server is really it defines the flow of messages through GeoEvent Server and the processes and conditions that are applied to the messages that propagate through GeoEvent Server. You configure this service in a service designer. This is GeoEvent Server Manager, and if you're familiar with Model Builder in our ArcGIS desktop suite of applications, this might not look terribly alien to you. You really, but instead of working with geoprocessing elements as you do in Model Builder, you're working with event processing elements such as processors and filters, inputs and outputs. The the role of an input connector, which is depicted here with the green rectangle, is to translate incoming streams of data into discrete messages that we refer to as GeoEvents. And the service has to have at least one input, but it can have potentially more than one input. Likewise, an output connector takes those GeoEvent messages and turns them into a formatted message that's appropriate for whatever destination it's going to, which could be an ArcGIS feature service, or it could be an email. So that's the role of the output connector. And similar to an input connector, you have to have at least one, but you can have multiple output connectors. Now, the bulk of this presentation is about what goes on between the inputs and the outputs, and that's the analytics. That's where the guts of all these processors and filters are going to perform their role. As GeoEvents propagate through GeoEvent Server, they're acted upon and analyzed by these inputs or by these processors and filters. The processors are represented by the yellow rectangles. And these are the components that interrogate the messages for certain conditions, or they might modify a GeoEvent message by adding fields or removing fields or calculating different values for certain fields. Or filters, which are represented by the yellow diamonds in this diagram, seek to halt the flow of certain messages if they don't meet certain conditions. They only will allow messages to pass provided certain conditions are present. And so by chaining numerous processors and filters together, you can put together a coherent set of steps to move a message through, provided it meets certain conditions, and then modifying it as necessary to meet your requirements and analysis. And that's what we'll take a look at in the following, in the next 50 or so minutes. Now, we won't spend any time talking about the inputs or the outputs. What we want to focus on here is are the processors. There are a number of processors that are included with GeoEvent Server right out of the box. So you can leverage a lot of these, and they're many and varied. Some of them seek to affect the geometry. There are projector processors and buffer processors that only work on the geometry, and others will calculate new values for certain attribute fields. There are also a number of processors that have been developed by people outside of our team. They might be other Esri groups, professional services, or whoever. They might be partners. Some of you might have developed your own, or you might develop your own processors. And you can do that because the GeoEvent Server includes a Java SDK that you can use to write additional capabilities for GeoEvent Server. And then you might share these additional processors in ArcGIS Online. So if you need a processor and it's not present out of the box, you might search. Maybe somebody's already written one that you could leverage for that. So here's a scenario that will hopefully illustrate a quasi real world example of how GeoEvent Server can process data. In this case, we have a construction site, and it's divided into a number of zones. Each of the vehicles is fitted with a sensor that regularly reports its location, as well as certain vehicle status, such as fuel level and so forth. Now, as the vehicles move around the construction site, we get regular updates of its current location. We also see on the map that we're archiving sort of a breadcrumb trail of where those vehicles have been. And you notice that when a vehicle moves from one construction zone to another, we get regular updates that that event has happened, has moved from this zone to that zone. In the case of the one vehicle that's actually moved outside of the construction site, that's a different level of alert. The different set of conditions have been applied there because it's a more urgent bit of information that they've completely left the construction site, and so that might be an alert that gets sent to a supervisor or something like that, rather than merely being logged in an information log. And it'll be important to this distinction in a few minutes that one of these filters look for whether or not that bulldozer is in any of these zones versus whether it has left all of them, is not present in any of these construction sites. And we'll make that distinction here later on when we talk about filters. So this is a representation of the GeoEvent service that defines the flow of messages that behind that construction zone scenario. So in this particular service, there are a number of processing threads that are occurring. First of all, as the vehicles they report their location and status, GeoEvent receives that information on the input and immediately forwards that information to an output. And this simply updates the map with the current, actually the last known location of that vehicle. Notice there's no processing step that goes on there. It's one message in, one message out. We're simply updating a feature layer at that point. However, the next step takes that last known location of the bulldozer and geotags it with the current construction zone that vehicle currently finds itself in. And this uses a geotag processor to do that. And it compares it with a geofence that we have there of the construction zones. And it outputs that location to our archive, so that this maintains that breadcrumb trail that we saw on the map. An additional processing thread here monitors when that vehicle moves from one zone to another. And we saw those updates appear on the map. It's moved from zone A to zone B. And that simply logs again, another message in our database, in our message log, so that we have a history of how much time it spent in one zone, when it moved to another zone. However, if that vehicle moves outside the construction zone, we have yet another processor, an incident detector, that says, hey, this bulldozer has completely left the construction site and this is a potential safety hazard, and that escalates a message right now. It sends a text message to a supervisor so that he or she knows that some urgent action needs to be taken. Now, this particular thread wasn't illustrated in the video, but it's certainly a possibility. In addition to the location of each of these vehicles, they might report certain diagnostic information such as battery level or fuel level. And if the attribute for fuel level indicates that the fuel is running low in a particular vehicle, that might automatically dispatch a message to a logistical team to get a fuel truck out to it and service that vehicle. So there are a lot of different ways that these processors can take a single incoming message and leverage it, analyze it for important information, and then react accordingly. Just a couple final words on processors. It's important to remember that some of them work only on the geometry of a message, and these might act to project it into a different coordinate system, or they might buffer it, or otherwise affect the geometry, and change it from a point to a polygon, because we support points, lines, and polygons in GeoEvents. Some of these processors can work on both geometry and or attributes. So in addition to affecting the geometry, we might also write in different attributes by calculating a certain value or concatenating strings. And there are a number of advanced functions for strings, dates, numbers, etc., that you can leverage when calculating fields. Some respond to certain conditions and then generate new messages. So in the case of that incident detector, for example, when certain conditions are present, and those conditions might be spatial and or attribute conditions, then it might generate an entirely different message rather than the vehicle status message that came into GeoEvent. So some processes will generate entirely new streams of data. But overall, processors tend to want to transform and forward a message within GeoEvent Server, and always processing in some way, but always maintaining and propagating that flow. And that's a little bit different from, actually entirely different from filters, which seek to arrest the flow of GeoEvent messages through the server. They will only pass a message when certain requirements and conditions are met. So this is a way to filter out a lot of the noise from a stream of messages, so that only the important bits of information get through and to further processing. You set up a filter with an expression, with one or more expressions, and these expressions, again, can operate on the geometry of a GeoEvent message or on the attribute, or both. You can add multiple filter expressions using and or operators, and negate them using not operators as well. So you can really put together some fairly complicated filtering expressions with filters. Now, in any case, when we've already mentioned that processors and filters can act on the geometry, and one of the ways they can act on geometry is by seeking spatial relationships between an incoming message and a certain geofence. So looking at that construction zone example, we would compare spatial relationship between the bulldozer's reported location and a set of construction zone geofences that we've already configured GeoEvent Server with. And the way we do that, let me back up one slide here. If you take a look at this expression, this filter looks for if the geometry of the incoming message is disjoint with all of a certain category of geofences. So in this case, we're looking at the delivery area category. And if the geometry is disjoint with all of the delivery area geofences, then that particular expression evaluates to true. But we want to make a distinction here, because we have another element of a filter expression, and that is the scope. And that's where that any or all come in that I referred to earlier with the construction zone example. So if your geometry intersects all of a given set of selected geofences, then that expression will evaluate to true. But in that case, it needs to intersect with every single geofence. In other words, those geofences have to overlap. Whereas if we say if the geometry is disjoint or intersects or any other spatial relationship with any of a selected set of geofences, then you can sort of see the distinction there. It only needs to evaluate to true for one of those geofences rather than for all of them, as in the first example here. So I'll illustrate that with a couple of diagrams here. In this case, let's look for an intersection between our GeoEvent and any of the selected geofences in our scenario. In this case, the flow of GeoEvent messages is represented by this string of points that we see here. So there are 1, 2, 3, 4 of those GeoEvent messages that intersect with any of these geofences. Whereas if we restrict it to intersecting with all of them, a similar string of GeoEvent messages represented by the points, only one of those points ever intersects with all of the selected geofences here. So you can sort of see the distinction between the any and all scope in a filter expression. Now, we've seen intersect and disjoint. There are a number of spatial operators that we can use here. Now, with the earliest release of GeoEvent Server at 10.2, ArcGIS 10.2, we supported only enter and exit and inside and outside of spatial operators. And these presumed really that the GeoEvent is going to be a point and your geofences are always going to be polygons. But as GeoEvent Server matured through additional versions, we expanded the list of spatial operators to include many more. So now we have a much broader host of operators that you can use. And also GeoEvents can be points, lines, polygons, as can geofences. So you could have a GeoEvent that's a polygon and find spatial relationships with geofences represented as points or polylines. And we'll see some examples of this in a little bit. Now, a word about geofences. Geofences exist as in memory within GeoEvent Server. And there are 3 ways to get geofences into GeoEvent Server, and they all start outside of GeoEvent Server. Now, 2 of them start as feature services. You can simply point GeoEvent Server to an existing feature service and have it read in the existing features that are part of that feature service. And then these become static geofences within GeoEvent Server. If the geometry for that feature service change at some point, GeoEvent Server doesn't know about those changes. And so you'll continue with the same geofences. And that could work to your advantage if you don't want them to change and keep pace, but it could work to your disadvantage if you do want them to keep pace. So in the second case where you want them to stay synchronized with that feature service, you can set up a regular synchronization where GeoEvent Server regularly checks back with that feature service, and if anything has changed, it re-imports those features to maintain a synchronization between the geofences in GeoEvent Server and the features within your feature service. So this is something that's most useful when the data in your feature service change relatively infrequently and at relatively low volumes and low speed. However, what happens when the data is changing at a rapid tempo, or you want to be able to respond to it much more quickly? In that case, GeoEvent Server can be set up to synchronize through essentially to itself. You can have messages coming into GeoEvent Server and then have them sent out from GeoEvent Server on a stream service as an output of stream. This leverages WebSocket technology to do so. You can then turn around and have GeoEvent Server have the geofences watching that stream. Might be its own stream, it might be on a different server though, so it doesn't matter. But you can have it watching that stream and generating and ingesting geofences from that stream. So this way, when messages are output on that output stream, we immediately have the geofence being updated with the new geography. So this is very useful for data that changes much more quickly. So let me illustrate how these dynamic geofences work. And this is an illustration not just of that output, the stream service scenario, but it could also work with a feature layer. If we have a stream of information that defines a location and that we subsequently define a polygon around, this could be a construction zone where they're doing some demolition and we want to control the airspace above it, right? So if something like that gets updated, or if we're watching the space and aircraft in the area don't intersect with it, if we're also watching a stream of aircraft movement in the area, we can determine whether or not there's any spatial relationship, any intersection there. But if at some point that watched area moves and we rebuffer that immediately then gets updated in our geofence, so that when aircraft following the same flight plan fly through the area, we now have the potential to be able to detect that set of conditions where, previously there was no problem, but now we have a spatial relationship. We have an intersection of events here that we need to act on. So this is a case where that synchronizing geofences with your changing information can be useful. Right now I'd like to turn it over to RJ, and we'll take a look at a couple of use cases.
Thanks, Ken. You guys are seeing my web map up on the screen? Good. So for this demo, what I'd like to do is simulate an onshore weather pattern. There is some sort of a storm cell approaching Southern California, and it has the potential to intersect with a set of critical assets, and we want to be able to detect that. Here in my GeoEvent Manager, this is the web app that you use to create your inputs, outputs, and GeoEvent services. You'll see that I have a couple of different services labeled Demo 1 and Demo 2. We're looking right now at that first process storm polygons. And you'll see that I have a couple of inputs here that are accepting data from the GeoEvent simulator over there to the left of the web application. I'm going to go ahead and start the first simulation. It's going to simulate a series of polygons coming into GeoEvent Server. And one is going to appear about every 2.5 seconds as I've configured it. You can see that that Demo 1 input is receiving data, and then multiple outputs are providing data out to a web map or some other client. If we want to take a look at what that looks like as an end result on the web map, there in blue you see the last storm cell that was simulated, and this is kind of the end result. So what I'd like to do is set the GeoEvent simulator back over, and I'm going to refresh my web map in order to remove all of the streamed services that you just saw. And then I'll step through the demonstration a little bit slower. You'll see that as the critical infrastructure is drawn in there and I simulate another storm cell, here's the storm cell polygon as it is advancing on shore. And if I pause here for a second, you can see that I'm displaying a couple of different bits of information. One, I have done a clipping operation, and I've looked at just the portion of the polylines that that storm cell is intersecting, but I've also managed to pull the entire polyline and highlight it in a buffer so that you can see kind of a scope or a possible extent of what the storm may affect. And as the storm progresses further inland, it intersects more and more of the electrical network, and we begin to see what the scope of impact might be for this storm. If I want to take a look then at the processors that went into this particular demonstration. Let's go back to the slides. Apologize, I thought I had that queued up correctly. There we go. No. There we go. What I'd like to do is take a look at the different portions of that GeoEvent service that were behind that demonstration. Set off here off to the left is the first and simplest portion of the GeoEvent service. It's taking the simulated data from the delimited text and sending it directly out to a tropical storm polygon's output. That's what's displaying that blue polygon on the map. Up here at the top, you see the Intersector processor and a field mapper. That is what is taking those orange segments of the polylines and creating a multi-part polyline that is able to be symbolized on the web map to show you just the portion of the infrastructure that's affected. The bulk of the service is actually using several different processors, what to use geotagging to receive, field splitter to cut it out into pieces, and field enricher to pull the information out of that feature service in order to do the buffering operations. So taking a look first at field mapper, this is probably one of the first processors you'll be using when you get started with GeoEvent. A field mapper is used when you want to change the schema or calculate a derivative value, add to your data. So the field mapper can translate from one GeoEvent definition to another. It's primarily used to flatten out the data if you have a hierarchical structure that is being received, say, as JSON or GeoJSON, and you want to output the data into a feature service, you'll first need to simplify or flatten out that structure. You specify how the attribute values map from one to another as part of the record. So if looking at this in Slideology, field mapper processor receives an event, has a track ID, a date, some sensor information, and maybe I want to just simplify that record. I don't want to broadcast all of that information out my stream service or in my feature records. So I use a field mapper to select just the track ID, date, and geometry and map those fields across to a simpler event record. Another processor is the field enricher, and I chose to use a field enricher from a feature service, though you can also do a field enrichment from a text file. The field enricher is what you use when you want to pull information from a secondary source and add to the data that you're receiving. An attribute join is how you conduct this field enrichment. It is not a spatial join. It has to have a primary key that is an attribute field such as a string or an integer. And then, as I said, it retrieves data from that secondary source to bring it into the event record. So here you see I have a track ID and a date, battery level. I'm maybe monitoring an ankle bracelet. And I have a secondary source that has information on who the first track ID is not allowed to contact. If for some reason I want to make sure that one person doesn't come in contact with another individual. So the attribute join occurs on the track ID. You see there the Victor 10987, and then enriches that information with the fact that he's not allowed to contact a Foxtrot 65432. And then the no entry is an additional piece of information. They're not allowed to enter a particular geofence or a particular zone that I'm modeling within my solution. A buffer creator does pretty much what you would expect. It creates a polygon around an event's point, line, or polygon geometry in order to enrich the event record with a new geometry. So you can either overwrite the existing geometry or add a second geometry to the event record. And this is an important distinction versus a feature record that you might be familiar with in a geodatabase that can only have one geometry and can only have one type of geometry. An event record has a geometry, one or more, and it's just another attribute. So I can have an event record that has points, lines, and polygons associated in it. If I want to put that into a feature service, that's where I'd use a field mapper to simplify that down and choose only one of the geometries. So here I have a point or a polyline that is coming in on the left, and I create a buffer about it. And then that buffer, you see, has rings, so that would be a polygon geometry that was produced on the output. And in this case, I chose to enrich the event record by adding that as a second geometry rather than overwriting the original event record's point geometry. The Intersector processor is another out-of-the-box processor that GeoEvent offers that clips or does the geometry extraction based on an intersection. So you use that to generate a geometry, as I said, that represents the intersection between an event record's geometry and a specified set of geofences. I was using it in the demo to create an intersection between the inbound polygon and a set of polylines that represented critical assets. The output of the intersector was a single multi-part polyline that represented that intersection. Geometry processors, all of them, can either enrich to add the result of the geometry or can overwrite the original event's geometry. So in this case, I received in some rings, a polygon. I determined the intersection there as the yellow square and output as an enriched event with the new polygon that represented the intersection. A second demo that I'd like to walk through is finding patterns in data. And for that, I'm going to open up a different web map. In this scenario, we're going to be simulating some crime data, and what I'd like to do is figure out how many crimes are occurring in a given cell within an analysis grid. So you see they're displayed on the web map. I have pre-created an analysis grid, and I'm going to begin simulating some crimes. Back in GeoEvent Manager, I'm going to go ahead and connect my simulator, and I'm going to start simulating crimes at a rate of about 10 crimes every second. And so what you'll see here inside GeoEvent Manager is I have crimes coming in here on my Demo 2 crime simulation. On the input, the GeoEvent Services is putting data out through a stream service to display them on a web map. So let's take a look at what that looks like. Here on the web map, you see that I start having incidents of crime showing up on the analysis grid. Now, before I actually start running the analysis, one thing I'd like to point out is something that is critical to this particular demonstration, and that is all of these crimes are actively being synchronized as geofences. Because in order to determine the intersection between the analysis grid and a second geometry, I would need to somehow cache or build a representative set of those geofences. So if I come back to GeoEvent Server and click on Site and come over to Geofences, you'll see that Right now I have some 600 crimes that have been actively synchronized. And I can hover over any one of these to show that it has a name, some sort of a unique identifier. But more importantly, it has a start time and an end time. If I'm going to be streaming data at any kind of volume or velocity into GeoEvent and automatically synchronizing a set of geofences, I want to have some way of identifying when those geofences are no longer relevant. And when the start time passes, or when the end time becomes in the past according to the server's current time, that geofence 1 will no longer be considered because it's not temporarily relevant, but it's also subject to be removed and deleted automatically by GeoEvent Server so it can maintain the geofences that it has in memory. If I switch back over to my Services tab to take a look at how the data is progressing, you'll see that I have about 1,200 crimes that have been simulated, and I can start the input down here that is pull grid polygon. And so what that's going to do is it's going to pull the feature service that has that analysis grid, and you'll see that it's going to pull about 1,500 of those feature records. I'm sorry, 5,100 of those feature records. And up here on the, I should have started this service so it actually did the analysis. Let's reset and pull those 5,100 polygons again. So now you see my demo 2 crimes by count is detecting that it has run an analysis on all 5156 polygons and found that 922 of those polygons contain one or more crimes. Now, this is a good first level analysis. And if I wanted to do nothing more than see an aggregation by counts, I could probably use the spatial temporal big data store. I don't have to set up an analysis grid and do any kind of expensive real-time analytic to determine how many crimes are dispersed over an area. But what I want to do is take this analysis to the next level and actually have GeoEvent Server alert me when there is a cell that has more than a certain threshold of crime. So when more than 10 crimes occur in any given cell, I would like to be alerted. And you can see here toward the bottom, my incident pattern stream is recorded that there are 5 of these grid cells that have high incidence of crime. So if I switch back to my web map, you'll see that I have some red flags now that are showing up. And I can come in here to any given flag, start to zoom in, and I can click on just the polygon if I was interested to see how many crimes occurred in that polygon. That was the first level analysis. But if I click on that incident flag, you'll see that I have an incident that is it has an opening condition of new count greater than or equal to 10. It is cumulative, it is ongoing, and it provides a description of how long it was ongoing. It was ongoing for the last 115 minutes and 41 seconds of demo time. So if I want to take a look then at some of the analytics that went into producing that demo, we'll switch back to the slides. So here I have the GeoEvent service that was behind that particular demonstration. If I want to look at the first bar, that is going to have a filter that says there are no intersections, there's no events. And I'll use a field calculator that's going to go in and calculate that polygon back to 0. That's because crimes have a time associated with them. The polygons have a time associated. And if I want to say there has been no crimes within the last 1 hour or the last 2 hours, I might want to clear the count off of that particular grid cell so I don't artificially alert based high crime because I'm continually counting over a period of days. So I test the count and then I use a field mapper to prepare the data prior to sending it out to the stream service. This portion of the GeoEvent service is detecting if there are any events, any crimes, any of the point geofences that spatially intersect one of the analysis grids. It uses a geotagger to go find that information and then actually does the count to put the count of the current crimes into that grid cell. The incident detector is what was configured as a processor to look at greater than 10 in order to produce the flag, and then so that entire bottom path there is streaming the flag incidents out to the web map. So let's look at the geotagger first as a processor that is used to detect a spatial relationship. You use a geotagger when you want to enrich an event record with information about a geofence with which it shares some sort of spatial relationship. The processor uses a spatial expression to identify related geometries, inside, outside, disjoint, intersects, and then adds the unique name of the geofence for every geofence in a set that satisfies that condition. So a geotagger can actually be pushing out a comma-separated list of geofences if more than one geofence satisfies the spatial condition for the point, line, or polygon that was received as an event record. It's essentially a spatial join. So I said earlier with a field enricher, that was an attribute join. The geotagger is providing our spatial join. So taking a look at what this looks like, if I have a polygon here that is designated Temecula Gangland, and I receive a point event that is within that area, I might want to do an enrichment on that event record to determine, well, what's the name of the geofence that it shares a relationship with. So highlighted there in green, is inside is an attribute field, and it now has the name of that geofence. The crime IDs is what is coming out of the geotagger. So to highlight that, if I had these 4 crimes that were in a given analysis cell, I'm receiving a comma-separated list. If I actually want to count that, there's some processing that I want to do on that comma-separated list. The first thing I'm going to do is use a field calculator to do a regular expression replacement. But to take a look at what a field calculator is, it calculates new values on a received event record. It uses an expression and is evaluated according to whatever attributes it is looking at. And the results can be written to a new field, or they can be written to an existing field. Typically, I will pre-map my event records prior to going through a field calculator so that I have an empty variable, if you will, as which to write the data, so that I'm not changing the schema of the event, I'm just writing data into an existing cell. So a field calculator with a distance of 105.6, maybe I want to convert that from miles or from feet into miles. So the field calculator's expression is a simple calculation, distance divided by 5280, and now the output event record has the distance expressed in miles rather than in feet. That first field calculator there is using, I said, a regular expression. So field calculator is probably one of the simpler yet more versatile processors that you can use because of the freedom that you have in the expressions that you construct. If you don't speak regular expression, that's fine. What I'm doing here, as you can see, is I replace all on the comma delimited list, and that regular expression pattern you see there says that I want to match anything up to a comma 1 or more times and just replace it with a comma. So basically I am destroying the comma delimited string by replacing all of the real information, the track ID values, with just commas. Then the second field calculator simply counts the commas, and it adds 1 because I don't have a comma at the end of the string. That's how I'm counting the number of items in that list. With that, I'd like to turn control back over to Ken, and he is going to walk us through some additional processors in a workforce tracking demonstration.
All right. Thanks, RJ. Thanks, RJ. So in this case, what I want to do is talk about, I'm going to show you this example of a field crew tracking scenario. So this is a case where a field crew is driving around or in their, the area that they've been assigned to do some work. And it doesn't matter what work they're doing, but the fact is they are reporting their location. They have a sensor on their vehicle that allows them to report their location. If they stop somewhere, it reports that they've stopped. If they send a message, they might send a text message or an email to somebody. So, and our system might log those messages. So we see the moving point around here where the crew is. We see a little pop-up there saying they sent a message at that point. Here's another message they sent. What it is. That message says that. Pop up. There you go. Inspection complete. Moving on. That first message was probably stopping to perform an inspection. If we stop the simulator at this point, essentially a flow of messages ceases, correct? And so we get an alert that, hey, we haven't heard from this crew in a little while. All right. If, however, we restart the simulator and we start to resume that flow of messages from the field crew, that condition closes. That we heard from them again. Maybe they just had to stop and change the batteries in their device, whatever. But this is a way that we can keep track of our crew, provide them some support, safety and security if need be, monitor their progress, making sure they're keeping pace with their where they need to be, not going where they don't need to be, and so forth. So I'd like to switch back to slides here, and we'll take a look at there we go. We'll take a look at sort of what the guts of the GeoEvent service are behind that scenario. So taking a look under the hood here, the process for each of these messages really begins when the crew sensor sends an automated location to GeoEvent Server. All right, the message is simply forwarded in the case of this first thread, this processing thread. The message is simply forwarded on to an output, and this is similar to what we've seen before with the bulldozers and with RJ's demos. That one, we're just updating the current location, the last known location for our crew. Now, if the crew happens to send a message as well, a text message or an email, we might be obligated to keep a communications log, so we can in turn output a stream of those communications messages, and including what message was sent and who the destination address was. And so that might be yet another output stream that we'll examine here. Now, there are a couple of use cases too where we're watching and we noticed that the crew stopped. In one case, they stopped to get some lunch and fill up with fuel and so forth. In another case, they stopped to perform an inspection of something that they're assigned to inspect, right? So in that case, they stopped moving. We continued to receive information about them, but they stopped moving. So that might be important information. Was there a reason they stopped moving? What if they're on a route, and they're not supposed to be stopped moving, but yet they stop? And that might be cause for, further inquiry at the very least. Why did you stop in the middle of the highway? Are they having trouble? Are they out of gas? Is there a traffic jam? Whatever that might be. A similar case is where we stopped receiving messages from those from the crew. And that might be a different case entirely. Did something happen to them? Are they no longer able? Was their device disabled? Did they have some sort of a catastrophic accident? Or did they simply, the battery get low and they needed to swap out, put some fresh batteries in, and then they're back on the grid? So these are the things that this service takes a look at. And I want to step through each of these processors in turn and look at what each one of them does. So the first of these is a field splitter. And this is useful in the case where they send a message. And that message might go to multiple destinations, right? They might include the text message for the supervisor, but also the email for the administrative assistant and whoever it might be. So when that message comes in, that the set of addresses actually would be a comma-separated list as an attribute in that GeoEvent message. So we use the field splitter then to take that comma-separated list from that one incoming message and split it up into two outgoing messages. Each one has one of those incoming addresses. And so the way then that looks in to use RJ's term in slideology, a message comes in, the addresses field has a pair of addresses in a comma separated list, and that field splitter then sends not one but two outgoing messages, and each one has exactly one address in it. And so this would work with 2, 3, 4 multiple values in that comma separated list. All right, now we want to take a look at the track gap detector. And conceptually, the track gap detector and the track idle detector work, by and large, very similarly. One just looks for a cessation of messages, the track gap detector. The other one looks for a cessation of movement of the incoming messages. So we'll just look at the track gap detector in this particular use case. Now, the track gap detector is simply it keeps track, maintains sort of a state and a memory of each distinct track ID that is tracking. And if at some point a certain period of time that you configure passes without it receiving an update from that track ID, then that triggers a track gap event. And so to illustrate this, we receive a message from a sensor. It has a particular track ID. This happens to be Victor 10987. And the track gap detector then logs that track ID and starts a timer waiting to see if either the timer expires or it receives an update. Well, if it receives an update like we just did before that timer expires, there's no gap. But then if that timer expires, continues or resets and starts ticking down and expires before we receive another update, now we have a gap condition. And that issues an output message that says where the attribute for that the attribute of gap equals true. This is the opening of that track gap condition. And then that timer resets and it continues to tick, and every time it elapses without us receiving another update from our track, it maintains that true condition of the track gap. And it issues another track gap message. Now, at such a point where we finally receive a new message from that track, if we ever do, the track gap detector then says, it closes that condition, gap equals false, and then we move on. And as long as we continue to receive messages from that track, that tracked asset, then the gap continues to remain false. So that's how the track detector works. What we do then is follow that with an incident detector. And we've already talked a little bit about this, but an incident detector simply looks at the attributes and or the geometry of an incoming message. And when certain conditions are true, it issues an incident. Now again, this is not going to be the same schema, the same GeoEvent definition as that track gap. It's going to be an incident definition. So the way this works then is it watches the conditions that it's set up to look for, and when those conditions evaluate to true, it issues an entirely new GeoEvent. This implies that it maintains state for that for that particular incident, so that it knows when the incident was opened, how long it's been open, what conditions caused it to open, and what conditions will cause it to close. So in this case, we have the same old notorious Temecula gangland, and when an event comes in, this event, if you notice the filter expression on the incident detector says if a certain track ID, if the geometry intersects with Temecula gangland, that's an incident that we want to report. Well, in this case, the point GeoEvent is that track ID that we're watching for, but there's no intersection, therefore no incident. Second message, same thing occurs. But with the third message, now we have an intersection of the tracked ID with that geofence in question, and now we have to open an incident. And you see what GeoEvent Server then issues is not that same incoming message, but an entirely new message that fits the incident GeoEvent definition, and it says that the status attribute is started. It gives you the time that that incident was opened and the condition that opened it, and then as well as the geometry where that occurred, the track ID of the incoming GeoEvent that triggered it, and then for each additional message, as long as these conditions evaluate to true, it continues to send update to that incident saying that it's ongoing, the duration that it's been ongoing, when it, and a lot of the same attributes such as when it was opened and the conditions, the opening and closing conditions and so forth. So finally, when that tracked asset moves outside, that closes the condition. Essentially, the opening condition is no longer valid. So it issues a new GeoEvent message, an incident message, but in this case, the status is ended. And again, it gives the duration that it lasted and some of the same additional attributes that it had before. And it will continue, it will no longer issue any updates as long as those opening conditions are no longer met. All right. Okay. Thanks. So the last processor I want to highlight here is actually a custom processor. And this is useful. This is a reverse geocode processor. Now, where this is useful is essentially in any case. If we want to send out an alert, for example, that incoming GeoEvent message has, we define it with longitude and latitude. But in many cases, if you want to be able to, if a person wants to be able to respond to that in some way, to go to that location and check it out, an address might be much more useful to that person. So we could, we could send the longitude and latitude, but this custom processor was written specifically to be able to take that longitude and latitude and send it to an external geoprocessing service and fetch the nearest street address to that longitude and latitude. So this, again, this is a custom processor written with the Java SDK, and uses the point geometry to return the nearest address. And it's configurable. You can set your own geoprocessing service, as well as the distance, the maximum distance you want to look to find an address. So the point comes in. It has no address with it, but it does have the geometry. We simply take that point, we send it out to the service, and what we get back then is a set of direction of address characteristics, the street address, the city, state, and various, the postal code, as well as the match address that sort of concatenates all of that information into an address string that you can actually use. And then this, in our use case, this would then actually go out to a text message or an email to the supervisor so that he or she knows where to go to respond to this particular case. So hopefully in this session we've been able to illustrate some of the ways that GeoEvent Server can be used to analyze real-time streams and to take a volume of incoming data and sort it automatically in real time to find conditions or to modify messages to be appropriate for your output destination and meet the needs for decision making and situational awareness requirements. There are some additional places that you can look for more information about GeoEvent Server. We have a number of tutorials online in the gallery in ArcGIS Online. There are also a number of blogs and discussion groups within the forums and video recordings. This session is being recorded, and we have other sessions that have been recorded in the past and are currently being recorded that delve more deeply into GeoEvent Server, not just about analytics, but about other characteristics and capabilities. We have a number of other sessions here at the Dev Summit this year about GeoEvent Server, not just about analytics, but all the other capabilities. So I encourage you to attend those and get a broader picture of everything that GeoEvent Server does. Finally, I'd encourage you to fill out the survey that we have for the session. That helps us improve this session for future conferences and events. So please do fill out the survey. We'd appreciate that. And at some point in the future, I don't know how quickly, but you'll be able to access this session in the proceedings and be able to review the PDF and maybe also the video for this session as well. So with that, I think we have no minutes left, but since it's the end of the day anyway, nobody else is coming in here. If you have questions, we'll be happy to answer them. Yes, sir. Two hands. Right here, sir.
Just one quick thing. Can you move back to the other proceedings? The other sessions. The list of sessions.
Oh, the list of sessions. Okay.
Yes, sir. Thank you.
Yes, sir.
So obviously we've seen that GeoEvent monitor building temperature, things like that. Is there a solution for looking at security cameras, footage, images, things like that? And the second corollary to that is, can the big data store be used to archive?
So the question is, can GeoEvent Server be used to ingest things like full motion video or video frames? And the answer is no. GeoEvent Server is primarily bringing in attribute data. Now, if your full motion video had keyframes and you had some pre-processing that was pulling out those keyframes and sending that as metadata, that's something that GeoEvent Server could process. But GeoEvent Server is not processing rasters, it is not processing images, it is attribute and geometry based. And then can the big data store be used to archive the full motion video or the video frames? Unfortunately, the answer is also no. That is strictly feature records. So the same way as you store feature records in a traditional relational database, you're storing feature records in the big data store, you're just storing a much larger volume of them and using a NoSQL technology as opposed to a relational table-based technology.
So I'd like to add to that too about video. While there's nothing out of the box, GeoEvent Server by itself doesn't do that. I have seen cases, I've seen demonstrations of Python scripts that integrate with video and external libraries that will essentially do shape recognition, feature recognition within video, and they identify people and cars and facial recognition, things like that. And that in turn generates, it can generate features. A point, here's a car, here's a person, things like that. So GeoEvent Server then could potentially be configured to watch that output from that system and then be able to leverage that information within GeoEvent Server. So it's not out of the box, but there are ways that it could potentially be made to work in a solution, including external components to GeoEvent Server.
One could imagine that a security camera that's motion activated triggers a still image.
Sure.
That's got a date time, it has a stamp, it's got an ID for that.
Right.
And it is Internet of Things.
Right.
That metadata that might come in.
In that case, if the camera were to take that still picture and place it, let's say it placed it in a folder, or if it's such a system that it uploads a raster and stores that in a geodatabase or something, whatever. GeoEvent Server can watch a folder for new files, or it can watch a geodatabase, a feature service for new features. So in that case, I think that the easiest way would be for it to watch a folder for new files, and when that camera deposits a new image there, at one point we had there was a custom processor. I want to say we being the GeoEvent team, but there was a custom processor out there that I saw that somebody had written that would crack an image and read the metadata, create a point and tag the image with the point, and you get where I'm going. So yeah, that kind of process could be set up. Sure.
Do we have any other questions? Well, we will still be here after this. I'm sorry.
Yes, please go ahead. Sorry.
So you showed a couple streaming services. Is there a good resource or blog or somewhere where we can find out where to find the streaming services for wildfire, earthquake, hurricanes, or anything like that that we could leverage in our map?
There's not a resource that I'm familiar with. If you are a partner or you have access through the EEAP to a technical advisor, that would probably be the best resource to turn to. We do have a internal slide deck that we maintain of success stories with GeoEvent, and if you reach out to the GeoEvent team, we might have some resources, but most of those are partner-specific solutions, like the Texas Department of Transportation and how they're using GeoEvent, and they wouldn't be providing their data for open consumption. Well, thank you guys very much for your time.
Thank you.